All right, IB AI SL2. Today we're going to go a little bit deeper with probability. We're going to learn some new notation. We're going to draw some Venn diagrams and come up with some probabilities. Before we get to our examples today, we're just going to look at some new notation. So this symbol right here between A and B is an intersection symbol. It means A and B. It's when events A and B both occur at the same time. The upside down version of the intersection symbol looks like a U, which is nice because I always remember U stands for union. But the upside down U doesn't really stand for that. Doesn't work out very well. But that means A or B. So the intersection is A and B at the same time. The union is A or B. And it can be both. It can be A or B or both at the same time. If you put a little apostrophe on an event, that means not A, the event that A does not occur. And then we're also going to talk a little bit about conditional probability, which is A and then a vertical line B. That means A given that B already happened. So I'm going to put in a little addendum here that this is A given that B already happened. Which I guess they kind of say here when B has occurred. Okay, let's do some examples using these. The first one, a student is chosen at random from this class. Oh, this is our same data from that last lesson I did with you guys where people are taking like the ESS class or the geography class or the Spanish class. So somebody's going to be chosen at random, and G is the event student takes geography. Then find these probabilities and interpret what they mean. This first part here, probability of E intersection G, or probability of G intersection E, which they're actually the same thing. So that's the first thing I want to say, is that E intersection G is the same thing as G intersection E. Now, what does that look like on the picture? If I zoom in here, G is this circle right here, and then E is this ellipse right here. So their intersection is only when they both occur at the same time. So if I was to use another highlighter, their intersection would just be this zone right here. It's only what they have in common, only what they share. So that's only one person out of a grand total of 11. I think if you add all these together, you get 11. So this is 1 out of 11. What that represents is the probability that a student takes ESS and geography. Part B. E union G and G union E, which means E or G. The union, if I go back to the diagram here, let me get rid of some of my markings. The union is all of E and G together. So it's all of this. It's the whole thing. That's what the union represents. So if you add all those numbers together, 2 plus 3 plus 1 plus 3. So first of all, E union G is the same thing as G union E. And this will be 2 plus 3 plus 1 plus 3. I'll fix that 3. All over 11, which is 9/11ths. Now what this is the probability that a student takes ESS or geography. Part C, the probability of E naught. Well, E naught if I was to shade on the diagram, here, let me get rid of this. E naught is everything outside of E. So if you kind of draw a line out around E and then fill in the rest of this, this is the area that is E naught. It's everything outside of E, which looks like about 5 people that are not taking ESS. So the probability of E naught is 5 out of the 11. Do we have to say what this represents? Yes. Student does not study ESS. Now, the last question, part D, is probability of E given G and then the probability of G given E. These ones are actually not the same thing. So let's think probability of E given that G happened. If you look at G, G is this whole circle right here. And we want to know the probability that E happened, or the probability of E given that G happened. So the way you need to think of this is that there's only 4 things in the pool because we already know that a student takes geography. So this is like the whole sample space of the problem. Now, out of those 4 people, only one of them takes ESS. So the probability of somebody taking ESS given that they take geography is 1 out of 4. So this is probability that a student takes ESS given that they take geography. Now, the probability of G given E, this is actually different. It's not the same thing. So if I go back to my diagram up here, and I get rid of all these markings, probability of G given that E happened. Well, if E happened, which means that the student does take ESS, we want to know the probability of them also taking geography. So it's still that one person in the intersection, but now the sample space is 1, 3, and 2 put together, which is 6. So I believe this is 1 out of 6. Here's what it means. So that's the probability that a student takes geography given that they already take ESS. All right, there's that problem. Next up, we need to define mutually exclusive. Now, you may have heard this word, mutually exclusive, before. I usually hear it in the real world when people are saying the two things are not mutually exclusive. Like if I was to say, you know, there's 2 kinds of people in this world. There's people who read books and people who drive cars. Somebody might say, Mr. Jolly, that's insane. I feel like those 2 are not mutually exclusive. Now, what they're saying is that there's some people who like to read books who also drive cars. They have some overlap in the middle. Mutually exclusive events cannot both occur at the same time. They can't be both. So the occurrence of one event excludes the possibility of the other. Classic example is if, like, you were to ask somebody how they got to school today. Did you walk or did you take the bus? It's not possible to have somebody that both walked and took the bus that day. You either walked to school or you took the bus to school. So they're mutually exclusive events. When events are mutually exclusive, the probability of their intersection, either way, A intersection B or B intersection A, is 0 because they have no overlap. If I was to draw a Venn diagram of it, it would look like this. Here's A. Here's B. No touching in the middle. A and A naught are complementary events, meaning, yeah, that's usually called the complement, A and A naught. They're always mutually exclusive of each other, because if you're talking about something that's not A and something that is A, there's no overlap in the middle. It's either A or not A. If you take the probability of A and then add the probability of not A, you will get the entire sample space, which is 1. It's like the probability of something happening plus the probability of something not happening is 100%. Like, it's the entire sample space. Next example. Katerina is exploring the names of students in her class of 15 students. Let's highlight that right there. 15 students. She sorts through the data from all the 15, and she figures out there's 2 kinds of people in this world. There's people with exactly 2 vowels in their given names. So here's the 2 vowel people. And then there's people with 3 vowels. Barbara. Look at that name. So, part A, we're going to represent this information on a Venn diagram, and then a student is to be chosen at random. So, if I start to make a Venn diagram of this, first of all, you always start a Venn diagram with a rectangle that is your sample space. Then, you need to decide if the 2 events are mutually exclusive or not. I feel like a lot of people, when they go to set up a Venn diagram, always do this. And they're like, well, that's a Venn diagram. There's always an overlap in the middle. That's not necessarily true. And it's not true in this situation, because if somebody has 2 vowels in their name and somebody has exactly 3 vowels in their name, there's no overlap. There's no person that has exactly 2 vowels and exactly 3 vowels in their name. So these are going to be mutually exclusive of each other. So we'll do one set here. For the 2 vowel people, we'll just call them A. Yeah, it says that they're A. And then another set for the 3 vowel people, which is B. So this is Clara, Tomas, Fengu, Rhea, and James. The other is Barbara, Akil, Melina, Daniel, Oliver, and Ricardo. Now, you guys, when I add up how many names we just did, I see that we have 1, 2, 3, 4, 5 in A, and then we have 1, 2, 3, 4, 5, 6 in B, which only adds up to 11 students, which means there must be 4 more students out there who don't fit into either of these groups. So I don't know what their names are, but we're going to call them Student 1, Student 2, Student 3, and Student 4. But there are 4 people outside of that group. So part A. We represented it with a diagram already. Maybe we'll just label this as A. Part B. Find probability of A, probability of B, and probability of their intersection. Well, the probability of A is 5 people out of the 15. So 5 out of 15 is 1 out of 3. The probability of B is the 1, 2, 3, 4, 5, 6 people out of the 15. So this, if you reduce it by 3, is 2/5. And then the probability of A and B, the intersection of the 2. Well, you guys, do you see how there's no intersection? Like, they don't overlap? So 0, because they are mutually exclusive events. State with a reason whether events A and B are mutually exclusive. So you can't have somebody that has, well, their probability is 0. So their probability of their intersection is 0. So that's the reason that they're mutually exclusive. Part D. Write down the probability of A union B. Well, that's both of the groups together. So here there's 5 people, and here there's 6 people. Add up a grand total of 15. So this will be 11 out of 15 together. That's that. Extension on this problem. Katerina further explores the number of siblings of the students of her class of 15. And she writes down another set in addition to those. So she's redefining and saying that group C is students with at least one sibling. So Alexandra, Isabella, Lucas, Paula, Oliver, and Ricardo all have at least one sibling. Draw sets B and C on a Venn diagram. Well, set B, if we go back up here, was Barbara, Akil, Melina, Daniel, Oliver, Ricardo. I see some repeat names in there. Like, Ricardo was in set B. So was Oliver. And I think that's it. Yeah. So those two are, they're in both. They're in Group B and Group C. So if I was to redraw this, and it says in the directions just to do it, with Group B. Oh my gosh, I am messing things up here. Just with Group B and Group C. Oh, you should always put the universal set in the corner, my bad. So Group B, we'll put here, and then Group C, there is going to be some overlap, so we'll put Group C. The people that overlap are Oliver and Ricardo. They were in Group B and in Group C, so we'll put Oliver and Ricardo in the middle. Then people that were in Group B that weren't part of Group C, if you look up here, are everybody else. Barbara, Akil, Melina, and Daniel. So Barbara, Akil, Melina, Daniel. Now, people that were in Group C that aren't in Group B are these new people here. Alexandra, Isabella, Lucas. Oh, yeah. So then the people that aren't included in this would be all of these people right here. So set A basically needs to go outside of this, which means outside we'll put Clara, Fengyu, Tomas, Rhea, and James. Okay, so there's the Venn diagram. A student is to be chosen at random. So how many people do we got here now? I think this should still be 15. Let's check. Why do we have 14? Hope I didn't mess something up. Let's see. Oh, I forgot Paula. My bad. Paula. All right, now we're back on track. Now there's 15 people. So part B says find the probability of B, the probability of C, and the probability of B intersection C. The probability of B is going to be all of the people in this zone, which is 1, 2, 3, 4, 5, 6 people out of the 15. So 6 out of 15, fully reduced, of course, is 2 out of 5. The probability of C is going to be all of C which is this entire circle, which is 1, 2, 3, 4, 5, 6. That's also 6 out of 15. Yeah. So that's 2/5 as well. Now the probability of B intersection C, their intersection, I'll use yet another color, is just this in between Z zone here. It's only their overlap. So that would be 2 people out of the 15. So that's 2/15, and that's fully reduced. Part C, are B and C mutually exclusive? No, they are not, because the probability of B intersection C is not 0. The probability of their intersection is this right here. It's 2/15. So because it's actually a number and not 0, not that 0 is not a number, whatever, they're not mutually exclusive. Part D, write down probability of B intersection, union, B union C. So B union C, if I was to use yet another color, would be the yellow, and it would be everything, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of the 15, which reduces down to 2/3. All right, you guys, this is part of section 7.3, but we're going to do the rest of it next class. Good luck. Ask me questions.